So we're going to go ahead and move on to our actual power computations. So the easiest way to start this is just go back to what our definition of power is. And what I'm going to do is write two sinusoids here. And I might use slightly different notation than your text, but I like this notation better. So I have a voltage that's Vm cosine omega t plus theta v, and then I have a current in the circuit that's same frequency, still a sinusoid, and it's got a phase angle theta I. Now, just going back to what we learned way back in our first electronics course, we know that power is just defined by as voltage times current. Now, what's different about the AC case, again, is that we're talking about it being multiplied as these, excuse me, as these time-dependent things. So let's just go ahead and write this out, though. This would just be Vm cosine omega t plus theta v times Im cosine omega t, whoops, I don't know why I wrote that on the next line, times Im cosine omega t plus theta I. So this is Vm times Im cosine omega t plus theta v times cosine omega t plus theta I. Now, we do want to get a little bit more handle on this right now, but before I even do that, we should make a comment here that part of the reason we don't like dealing with instantaneous power is that depending on what time is, the power could actually be zero, because there's clearly going to be a value for t that I could put in to make this cosine zero, which then doesn't matter what any of these other terms are because you're multiplying by zero. And so we don't really like the idea that, oh, well, you have zero power, because, well, we know that AC, it's not that you're given zero power. Maybe at one instant in time there's zero power, but we really want to think about, like, well, on average, what's the power being delivered to the circuit? So we need to kind of manipulate this a little bit here. Now, if you go back to a trig course, and you might say, oh, I hated trig, or maybe you love trig. I actually really liked trig when I took it. There was part of trig that most people don't enjoy, but it was with the identities, where you have a bunch of identity formulas. And the thing I don't like about trig when the way it's taught sometimes is sometimes teachers say, oh, why do you need to know these trig identities? Well, because it's useful, because you can compute angles at different things and you can get the precise values, and all of that's crap. Or if they even just say, oh, well, it's good to know because, well, you need to know it. That's a load of horsepucky as well. The real reason you need to know trig identities is for when you encounter situations like this, and you're like, okay, I'm going to try and get a better handle on this. And look, I've got two cosines multiplied together. I have a trig identity for that. That's cosine of a minus b. Sorry, let me write this correctly. 1/2 cosine a minus b plus cosine of a plus b. Now, it doesn't necessarily look like that gets us on a handle on it too much, but I'm not going to go through the details. You can go through and do the computations here or show all the work. I'm just going to write what our result is. We have 1/2 Vm Im cosine theta v minus theta I. Plus 1/2 cosine 2 omega t plus theta v plus theta I. And of course, these units are all in watts. But what do we have here? Well, what we now have, just doing that simple computation here, we have here this term is time independent. Notice there's no t in this equation anymore. So this is going to be some kind of constant. And here, this, of course, does matter with time, but we should notice here that this is a periodic still. But there's two ways to think of this. A lot of textbooks like to say the period is doubled. I like to think of it as the frequency is doubled, which is the same thing as saying the period is doubled. But the frequency of the original current and voltage has doubled in this power here. So if we were actually to graph this, the power would have a DC offset, and then it would be a sinusoid still, but it would be at twice the frequency of the voltage and current, which is all well and good. Now, from this, we're like, okay, great, so what do we have here? Well, this term, this first term here, is so important because it's constant. We actually define this to be our average power. So if we want to know what is the average power, delivered to a circuit, it is capital P is what we call this, and this is 1/2 V sub m I sub m cosine of theta v minus theta I. So this is an important equation. And we can always find this, but we're going to try and figure out quicker ways of getting to this answer here. But before we do that, I want to rewrite this one way, because remember in the previous video we talked about effective values. And notice 1 over 2, I mean, it seems weird to split it as 1 over square root of 2 times 1 over square root of 2. But hopefully you all agree with me that 1 over square root of 2 times 1 over square root of 2 is 1/2. And then we have Vm times Im still. But wait a minute here. If I think about this, this is just V effective. And this term here is just I effective. And so we get here that another way to write this is that it's the effective voltage, or the RMS, cosine of theta v minus theta I. And I'm just going to rewrite this in both notations, because remember, RMS is the same thing as effective. And so we have another set of equations here that are useful. But what's key to important to point out is these equations are slightly different. One equation has this 1/2 and the other equation doesn't. So how do you know which equation to use? Well, that's where you need to read the problem carefully. Does the problem give RMS or effective values? That's what you need to ask yourself. If the answer is yes, that it gives you RMS or effective values, clearly you use these two equations. If the answer is no, meaning that nowhere in the problem does it say anything about RMS or effective, then you go back and use this equation up here. Now, before we move on here, there's actually there's a lot of important things that we end up getting out of here that we define. There's something else that's important in here. This cosine of theta v minus theta I is actually going to be something important. We're going to come back to it, but I'm just going to mention it right now. This is something that's called the power factor. And what this is going to actually tell us in more detail, we'll learn this later on, is how much average power are we getting as compared to the apparent power that's being delivered. And we'll talk about what apparent power is in a little bit. Now, we want to come up with ways to compute this here. Well, let's look at an example here that are pretty easy here. So let's look at a couple pretty quick, easy examples. Or at least one easy example here. So let's just say the voltage is equal to 3 cosine omega t plus 30 degrees. I is equal to volts. 1.5 sine omega t plus 120. Let's saying 120, let's do 140 degrees amps. What is the average power? Well, first off, we need to recognize the fact that I am given non-RMS values. There is nowhere does this say anything about these being effective or RMS. How would you know? Because it would say something like volt RMS, amp RMS, or volt effective, amp effective, or it would put it on here like RMS. So there'd be some clear indication that these would be RMS values, which they're not. So we know we need to deal with the power equation to find the average power being 1/2 Im Vm cosine of theta v minus theta I. Now I did this kind of problem on purpose here because let's go back to how we computed this here. At the beginning, notice here, both of these were cosine functions. So I need to make sure that I have cosine functions for both of these. Well, I have a cosine function for the first one, but for the second one I don't, but that's not a big deal because we remember that we can rewrite the sine function as a cosine function, but with a phase shift. And so we get that this current is actually equal to 1.5 cosine omega t plus 50 degrees amps. So now we can just go ahead and do what we call maybe our formula plug and chug. So we'd have 1/2 Im is 1.5, Vm is 3, and then I have cosine of 30 degrees. Now it does matter the order you put these in. It's theta v minus theta I minus 50 degrees. So this is going to be 1/2 1.5 times 3 times cosine of negative 20 degrees. And let's go ahead and do that computation. 1.5 times 3 divided by 2 times 20 cosine. And so we get 2.11. And the units for average power are still watts. So we get 2.11 watts for this situation. Now you might say, well, okay, that's great. How does that help me with a circuit? Well, it really does help us with a circuit because circuit analysis, we can always find voltage and currents. And with steady state analysis, we can always find the voltage and currents using steady state analysis. So we can just go ahead and simply find these equations for the voltage and current. Now we're going to learn easier ways to do that and quicker ways to do that. But to finish up this section on average power and instantaneous power, as I said, we want to come up with easier or other ways to do this. One way we can do this is that power is equal to 1/2, and I'm not going to go into mathematical details of this. And I'm doing these bold here on purpose because these are phasor voltages and currents. But this is the voltage, phasor voltage, times the conjugate of the phasor current. That's what this is right here. And then we just look at the real part of that answer and multiply it by 1/2. That is another way to get us. And so this is actually going to lead us to some additional formulas in the next section on how we can do this and do circuit analysis to find average power being dissipated by a component.